Assalamu alaikum wa rahmatullah. Welcome back, my dear students, in part 2 of Kinematics II, which is the last part of chapter 7. At the end of this part, you will be able to determine the characteristics of the uniform circular motion. Before, let's remember the main ideas of the previous part. The curvilinear abscissa S of t describes the position of a particle in a curvilinear path. The average velocity is given by delta S divided by delta t. The linear velocity is the derivative of the curvilinear abscissa, and the tangential acceleration is the derivative of the linear velocity. The angular abscissa is given by theta, the angular velocity is given by theta prime, and the angular acceleration is given by theta double prime. The curvilinear and the angular quantities can be related through S is equal to r theta, V is equal to r theta prime, AT is equal to r theta double prime, and AN is equal to r theta prime squared. Let's define the uniform circular motion. In a uniform circular motion, the magnitude of the velocity vector is constant. V changes in direction. The angular velocity theta prime, which is equal to V divided by r, is also constant, and its derivative, which represents the angular acceleration, is 0. Theta double prime is equal to 0. In a uniform circular motion, both the tangential and the angular accelerations are 0, therefore AT is equal to 0 and theta double prime is equal to 0, and only the non-zero acceleration is the normal acceleration, therefore A is equal to AN. In a uniform circular motion, the particle moves with a constant speed v, thus each cycle takes equal time called the period t. Therefore, the uniform circular motion is periodic. During each cycle, the distance covered is delta S, which is equal to the perimeter of the circle, which is equal to 2 pi r. So the time taken to complete one cycle is the period t. How can we calculate this period? We use delta S is equal to v times t, then t is equal to 2 pi r divided by v, which is 2 pi divided by theta prime. Therefore, omega, or theta prime, is equal to 2 pi divided by the period t. We can also write the period t in terms of the frequency. It is of the form omega is equal to theta prime, which is equal to 2 pi f. Let us now solve the following example about the uniform circular motion. The average distance between the Moon and the Earth is 384,400 kilometers. The Moon rotates around the Earth once each 29 days. Determine the average speed of the Moon as it rotates around the Earth. Suppose the rotation of the Moon around the Earth is circular. We have to use v is equal to 2 pi r divided by the period t. We convert the period from days to hours, and then the final answer is 3,468.43 km per hour. Let's now study some applications on uniform circular motion. In certain technical objects, it is sometimes useful to transmit a motion from a part to one or more parts. For example, in meshing gears, the gears turn in the opposite direction. S1 of t is equal to minus S2 of t. Transmission chain, the gears turn in the same direction with S1 of t is equal to S2 of t, and coaxial gears, the gears turn in the same direction with theta 1 of t is equal to theta 2 of t. We are going to explain each of the following examples.
First, what is a gear? A gear is a rotating circular machine having teeth. Let's talk about meshing gears. A meshing gear is usually composed of two gears in contact, meshed with each other, so that one of them is capable of driving the other. Using this figure, verify that S1 of t is equal to minus S2 of t. The positive sense of rotation is chosen anticlockwise. From the figure, we can notice that theta 1 is equal to pi. To calculate S1, we use minus R1 times theta 1, which is equal to minus pi centimeters. From the figure also, we notice that theta 2 is equal to pi divided by 2, then S2 is equal to pi centimeters. Therefore, S1 of t is equal to minus S2 of t. Theta 1 R1 is equal to minus theta 2 R2. By deriving this equation with respect to time, theta prime 1 R1 is equal to minus theta prime 2 R2. Therefore, theta prime 1 divided by minus theta prime 2 is equal to R2 divided by R1. Notice that by rotating gear 2 anticlockwise, it can be seen that gear 1 turns in the opposite direction. Also, small gear 1 spins faster than the big gear 2. Since R1 is less than R2, then the absolute value of theta prime 1 is greater than the absolute value of theta prime 2. Now let's talk about a transmission chain. In a transmission chain, the two gears are not in direct contact but connected to each other using a transmission chain that prevents slipping. Using this figure, verify that S1 is equal to S2. The positive sense of rotation is chosen clockwise. S1 is equal to R1 times theta 1. Using the figure, we know that theta 1 is equal to pi, then S1 is equal to pi centimeters. S2 is equal to R2 times theta 2. Also using the figure, we can notice that theta 2 is equal to pi divided by 2, then S2 is equal to pi centimeters. Therefore, S1 of t is equal to S2 of t, theta 1 R1 is equal to theta 2 R2, and therefore theta prime 1 divided by theta prime 2 is equal to R2 divided by R1. Notice that in this case, by rotating gear 2 clockwise, it can be seen that gear 1 turns in the same direction. Also, the small gear 1 spins faster than the big gear 2. Since R1 is less than R2, then theta prime 1 is greater than theta prime 2. What about the coaxial gears? Usually in a coaxial gear, the gears are connected by an axis of transmission. Using this figure, verify that theta 1 is equal to theta 2. The positive sense of rotation is chosen clockwise. We know that S1 is equal to the perimeter divided by 4. The perimeter of the circle is equal to 2 pi R1. Therefore, by using theta 1 equal to S1 divided by R1, we can find that theta 1 is equal to pi divided by 2 radians. S2 is equal to pi centimeters, then theta 2 is equal to pi divided by 2 radians. So theta 1 is equal to theta 2 and theta prime 1 is equal to theta prime 2. Pay attention that by rotating gear 2 anticlockwise, it can be seen that gear 1 turns also in the same direction. The small gear 1 and the large gear 2 rotate with the same angular velocity, where theta prime 1 is equal to theta prime 2. Now in this slide, you are going to see some rules which are related to the meshing gears, the transmission chain, and the coaxial gears. These rules may help you in solving the problems which are related to the gears. In this example, we are going to explain the functioning of the solid spinner. How can we explain the functioning of this object? The yellow gear is the one that you spin. It will drive the first red-toothed gear, which will turn in the opposite direction, but much faster since it is smaller. Then theta prime red 1 is greater than theta prime yellow. The second red gear will rotate at the same speed as the first one, but in the opposite direction, same sense as the yellow gear. Then theta prime of red 2 is equal to theta prime of red 1. Then, through the transmission axis, the pink gear will also rotate at the same speed and in the same direction as the second red gear. Then theta prime pink is equal to theta prime red 2. So the pink gear spins faster and in the same direction as the yellow gear so as to rotate the basket and dry the salad. Theta prime red is greater than theta prime yellow. Let us now sum up. In a uniform circular motion, the magnitude of the velocity vector is constant, v changes in direction. In a uniform circular motion, at is equal to 0, theta double prime is equal to 0, and a is equal to an. Uniform circular motion is periodic of period t is equal to 2 pi divided by theta prime, and angular speed theta prime is equal to 2 pi f. For meshing gears, S1 of t is equal to minus S2 of t. For transmission chain, S1 of t is equal to S2 of t, and for coaxial gears, theta 1 is equal to theta 2. It's the end of this part and the end of chapter 7. Thank you for watching all the videos.